Hello and welcome to the video lecture on denormalization. So during the logical database design process, when we were setting up our ERDs, we followed a methodology called normalization, and there are, for the first normal form, the second normal form, the third normal form. We basically stopped at the third normal form. We did that in order to avoid data anomalies, whether due to updates or inserts or updates, deletes, and inserts. So now we're going to talk about what's known as denormalization, and we denormalize due to performance reasons. So again, the benefit of denormalization is that it can improve performance by reducing the number of table lookups. So every time, and we'll get into this with SQL as well, every time that we have to join tables together, right? So if I want to see the number of students that are enrolled in a course, that's going to require that I bring in the student table, say an offering table, an enrollment table, and a course table. So there are 4 tables, all of which have to be joined together. So that's going to require some performance. That's going to be a performance hit to join all of those tables together. There is a cost associated with denormalization in that now I have duplicated data, right? So now I'm going to be storing data. In a fashion that is against normalization, hence the word denormalization. So I'm going to have wasted storage space. And since I'm doing this, I'm going to set myself up for the possibility of data integrity problems, right? I can have update anomalies and insert anomalies and deletion anomalies. And that's a cost because I'm going to have to put something in place to keep that in place, all right, to keep the data consistent. When we talk about denormalization, there are usually opportunities for that, and we're going to go through a couple of these opportunities. If we have one-to-one relationships, in other words, if we have supertype subtypes, for instance, and we have one-to-one relationships, that's an area where we can consolidate our data and denormalize. We can have many-to-many relationships with non-key attributes, right, associative entities, and we'll go through an example of that. And we can have reference data, where one side has data not used in any other relationship, all right, and that's where we talk about lookup stuff. So let's go through some of the examples. So here we have a one-to-one, right, so a student will submit an application, and if a student submits an application, so we have our ERD, right, and then that gets into, we change that into the relational model, so we have normalized relations, and we see that the student ID becomes a foreign key in the application, right. Then what we can do is, instead of storing that application ID, the foreign key to the student ID in the application table, we will merge them together, so that we have the student table now keeps track of the application data and the qualifications. And again, this is perfectly normal in physical database design. We normally normalization. We normally wouldn't do this during the logical database design. This usually occurs when we're dealing with performance. So another scenario, right? We have a many-to-many with non-key attributes, right, in our an associative entity. So we have our vendor, our item, and our price quote is our associative entity. We look at the relational model, and we see that the price quote has price, but in order to get that, we have to merge the tables together. So another way of doing this would be to merge the price quote and the item table, where we still have the vendor, and the vendor stands by themselves, but now we have a table called item quote, where we store the vendor ID and the item ID. The combination of that is the primary key, so that, for all intents and purposes, becomes an associative entity. and then we have our description and our price. Notice that we can have nulls in the description, so that's a possibility. So again, wasted space. And then we have a scenario where we have a lookup, right? So we have storage instructions, then we have an item. So we've got our normalized relations where we have storage, where it's stored in the container type, and then we have our item, which has a description, and then the instructions ID, and then we'll just merge the two of them together so that the storage information where to store it is actually part of the item record. And again, that's what physical database designers get into, this kind of stuff in order to increase performance and actually physically design the database. And that is the end of the denormalization